Okay, so let's carry on with this. So just maybe as a tiny little better illustration here of the meaning of this one. So let's do the following thing. So here, what am I doing? I'm just going to do yet another like fantastic drawing. Where I've got a series of dipoles, right? So I've got a little dipole here, and then as I move along in this direction, I've got a bigger dipole, and then I've got a bigger dipole like this, okay? So let's just imagine that I'm walking through my material in this direction. And what do I mean by these dipoles here? Well, here there's a little bit of negative charge here, a little bit of positive charge here. Here there's somewhat more negative charge and somewhat more positive charge. And here there's really more negative charge and more positive charge here. Okay, so as I move through my material here, my dipole moment per unit volume increases. And then what I can do is just look locally at the way charges compensate each other. You see, so if I look here, I've got my little dipole followed by a bigger dipole. So that means that here, the negative here would be bigger than the positive here. So it's as if I had an accumulation of negative charge. And the same thing occurs here. You see this negative charge here coming from the tail end of that dipole is bigger than the positive charge here coming from the head end of that little dipole. And that is why the density of bound charges goes like minus the divergence of the polarization. Minus, because you see, as my dipoles increase here, as I move here, I've got more like negative charge on this end, positive here. Okay, and divergence is just that, you know, that works in all directions I can move into. Okay, so I mean, does that like drawing miraculously clarify that? Okay, so that's, you see what I mean, right? With these like increased question, yes. So when we compute the dipole, it's essentially the summation of charge times distance, right? So if I have plus minus, then my dipole moment is that way. So here the arrows that I have are really like local dipoles, like this, okay? So yeah, these are not the electric field lines, right? These are really the formulas for the dipole moment that we have. Once again, so sum over positions of the charges of charge times position of the charge. So then positive charges contribute positive, okay? And then the surface term, if you want, comes from the uncompensated charges at the boundary. Okay, so just the value of the charges there. Okay, so there is, I mean, maybe what I'm going to do is I'm going to ask you to look at the example in the notes. So it's example 4.2, which is the electric field of a uniformly polarized sphere. Okay, so maybe, I mean, I could do it in class, but then I can't do the other stuff. I mean, you've got the notes, right? You found the notes on Canvas. I put these PDFs with the notes I use here, so they're there. It's one of the examples in there. So essentially, what you will see is that so you have a sphere which is uniformly polarized. What do we mean by this is that P is constant inside the sphere. Okay, and so check it out for yourselves. it's not that complicated. It's just really applying what we do with a result of another thing in the notes from when we did the multipoles. But what you obtain is that is the result is that if you've got this sphere like this, yeah, I mean, it's not too bad. So the sphere has these. If I just plot the electrical field, yeah, it would go out like this, and then it would go like this, and then like this. Well, this one should be straighter. Okay, so that's the way it kind of looks. And inside the sphere, magically, the field is absolutely constant. Okay, but you can compute that. So the idea is that you just use the expression that that I gave you, right? So I give you the polarization, which is constant inside the sphere, and then you can compute the bound charges. You see the bound bulk charge is 0 because P is constant, and then there's only this thing at the boundary. So P dot n, the n vector, is just the unit vector on the surface, right? So it's just, if you've got a constant vector, there's just a cosine of theta. But I'll let you look at that example in there. Okay, the idea is that if I give you the polarization, you can compute these charges, these bound surface and bulk charges, and with that you can compute the actual potential. Okay, and then if you have questions about it, then we can talk about it next week. Okay, another thing which is, perhaps, I mean, it's beautiful but slightly academic, is the section on the field inside a dielectric. Again, I'll let you read this by yourselves. It's a slightly subtle argument. So in Griffiths, it's subsection 4.2.3, the field inside a dielectric. Okay, what this thing does is actually carefully answer the question or the objection. Yeah, but what happens really microscopically? Can I really write this equation for the potential? Because if I'm inside the dielectric, as I move about, sometimes I get arbitrarily close to positive charges or to negative charges. So is the expression that you write here still valid? Okay, and the answer is that yes, it is still valid. Okay, but the reason is slightly subtle, and I would say this is not exam material in the sense that in the exam I wouldn't ask you to rederive or to use this result here. However, I encourage you to have a look at it because there are a few interesting sub-steps associated to it that are quite interesting. Okay, so but the end result is that the expression that we started with at the very beginning, so this one here is just entirely correct, even if we go to microscopics, okay? Because at any point in the material, of course, I can just get the potential dominated by things at a certain distance. So if I have any notion of averaging, spatial averaging of these things, then I'm automatically correct. Okay, so it's a bit subtle, but we can just leave it at that. Please have a look at it, but it's not going to come back to haunt you at later points. Okay, instead I'd like to move on to introduce the kind of almost converged and final way of doing electrostatics in matter by introducing the concept of the electric displacement. Okay, so let's just do that. So this is now on page 4, 9th page of chapter 4. The electric displacement. So what is this? So we had the following thing. We had that if I have a polarized object, then I get a spatial density of bound charges, which is minus the divergence of the polarization. And I get at the surface this set of bound charges, which is just the polarization dotted into the unit vector at the surface. Okay. So the meaning of this B here are that these are bound charges. And what that means is that these are things that you can't really, remove or add with your batteries and stuff. These are things that are stuck to your material. It's your material that carries these charges. And of course, by doing some external things on it, you can displace these things, but they remain bound. Okay, so whatever charge you had in there, it can move around the material, but you cannot add to it or remove to it. That's why they call it bound. If you want it, it's like atoms or molecules deforming and stuff. You're not going to break apart the molecules or anything, right? You're just going to polarize them a little bit, but these charges are bound. Okay, and to distinguish the charges that you will put in the system, then what we do is we use another letter. We use the F for the free charges. Okay? And these are, if you want, unmovable in contrast to the so-called free charges. Okay, so if I were to come and inject charge in my material, what I would do is I would add what I would call the free charges to the material, and then the total charge density within a dielectric is there's rho bound plus rho free. I mean, it sounds like a political discourse, but yeah, that's not what it is. It's really just like, okay, so you're either bound or you're free. Okay? Now, what we can do is go back to Gauss's law. And what did that tell us? Gauss's law tells us that the divergence of the electrical field is equal to charge density divided by epsilon 0. Okay, so I can write, again, if I get my electricity back, yes. So epsilon 0 times the divergence of the electrical field is equal to the local charge. But the local charge, that's interesting. My tablet is going mad. The local charge is this rho bound plus this rho free charge. But this rho bound, we've just said that it was equal to minus the divergence of the polarization. Okay? So what we get really, if I bring this term to the other side, what I get really is that the divergence of epsilon 0 times the electrical field plus the polarization, this is equal to rho free. Okay? So what does that mean? It means physically I've got my system, I've got my dielectric, I come and I plug some battery, I put some voltage difference somewhere, I push charges, free charges. Those free charges create an electrical field. But those free charges also create a polarization. Okay? And this polarization contributes to the electrical field, if you want. Right? It all adds up. It's like a resonating thing, right? One influences the other, and it's just like a response of these things. However, the only things I can control are the free charges. So what I can do is, by playing this trick, I can now define an object that is called the electric displacement, which, magically will have the symbol D, okay, that then obeys a Gauss-like equation, but only with the free charges as source terms. Okay? So D is equal to epsilon 0 times the electrical field plus the polarization. And this thing then obeys a kind of Gauss-like law. Divergence of D is equal to rho free. Okay, and I've just put the epsilon 0 there, so it's kind of easy. Okay, so this is, if you want, Gauss in matter. Okay? You'll see there are a few subtleties associated to that. So you could also have the integral form of this thing, which would be that if I take a surface integral enclosing a certain volume of D, so I'm just literally using the divergence theorem of this, then I get the total free enclosed charged. Okay? So the free charge is not the total charge, because the total charge is the free charge plus the bound charge. Okay? But if I know the free charge, I can determine the displacement like this. Okay? So just to illustrate the utility of this, so example. What we're going to consider is an infinite wire with line charge density lambda as usual. This is really charge per unit length. And we will say that this is surrounded by some rubber, let's specify it's rubber, some rubber insulation up to radius A. And the goal is to find the electric displacement. Okay, so rubber is a dielectric. It's a relatively poor dielectric, but nonetheless it is a dielectric. So what do? So we have our wire, and again with my fabulous drawing skills, so I've got the rubber cylinder around it. It's like it's coaxial, of course, as you can see. It's absolutely perfect through the middle of this bulk rubber. So this is like bulk rubber. Okay, and we want to know how the electrical field looks like, but first we want to compute the displacement field. Okay, so what do? Well, we go back to the Gauss form that we have here for the displacement. Okay, so what I'm going to do here is I'm going to consider a surface, a cylindrical Gaussian surface along the wire. So let me, let's imagine that I draw another cylinder like this. So this is my Gaussian surface. Okay, and what I do is that I integrate the displacement over all the surface of this cylinder. Okay, now the wire is infinite, so we expect electrical fields to be radial. That means that there's no contribution from the ends of my Gaussian cylinders. So the only contribution comes from the surface around here around. Okay, so what does that tell me? If I integrate this thing to, let's say this is radius S, so this is my Gaussian surface. Okay, so from Gauss, okay, what I get is that, so D is going to be constant over the whole surface. So that's going to be D. The whole surface is, let's say I have a certain length L here. The whole surface is 2 pi S times L. And this has to be equal to the free enclosed charge. But the free enclosed charge is just the line density times L. Okay? So this has to be equal to lambda L. And that means that, putting back the vector, so my D here is equal to lambda over 2 pi S. Okay? And it's going to be in the radial direction, right? S hat is just radially coming outwards. Okay? So that's my displacement. Yes?
Why does lambda not include the bound charges?
So lambda here, what I mean here is the line free charge density. So that means it's the charge that you put in by hand from your battery. And you tell me exactly how many coulombs per meter that is. And now, of course, when you put this charge in this wire, the rubber will polarize. Okay? But the free charge density is really the one you put in. Okay? So the thing that occurs, of course, is that I've got my lambda here. If I did not have the rubber, it would be the problem we've solved before, okay, where the electrical field is just lambda over 2 pi S. But now I've got rubber, so I'm giving you the displacement. Okay? But the rubber, of course, has an accumulation of like negative charges if lambda is positive. Yeah, so the rubber would polarize, so there would be negative charge going close to the little wire, and then positive charge accumulated at the outside. Okay, so that that would like change the field that you see. But now the fun thing here is that this is the solution that we have everywhere. Okay, this is both valid inside the rubber as outside of the rubber. Okay? So if we have, so outside the rubber, we know that outside the rubber, the polarization is equal to 0. So then the electrical field is just 1 over epsilon 0 d outside, and that's just lambda over 2 pi epsilon 0 s hat, okay, for s greater than a. So inside, we don't know E. Because we don't know P. Okay? So we don't know E because we don't know P, but we know D. All right? And that's kind of good enough. Okay, to find out the polarization, maybe we need to make some more measurements and do some more complicated things. Okay, but that's the idea. So typically, sometimes even calculations like that with these dielectrics, they look even just as simple as calculations in free space, because you can use the equivalent of Gauss's law. Okay. Now there's a little note of caution here. Okay. If we had just the electrical field, you remember that if we take the curl of this, then we forget about it. But this is not true of D. So the curl of D does not necessarily vanish. Okay, in fact, if we calculate it, so the curl of D is the curl of epsilon 0 E plus P. So this one's 0, but the polarization's curl does not necessarily have to vanish. Yeah, not always 0. Okay, so you have to be a little bit careful when you manipulate these things. The displacement field is not exactly like an electrical field. It can sometimes behave in strange ways, but nonetheless, the equation that we wrote, the Gauss equation here, this will be always valid in the case of electrostatics. Okay. Now maybe a couple of other notes. Yeah, let's see how far we got. Not too bad. Okay, so just a little note on boundary conditions. Again, I'll let you look at the notes for that. As usual in electrostatics, what we're doing really is solving like Poisson's equation or Poisson-like equation in the presence of boundary conditions. So see notes, and especially the book that has the explanation. So the boundary conditions that you have, if you have a surface and you do the perpendicular above, so these look just like the conditions that we had before. Okay, except that now you remember, so in the electrical case, this was really just the charge over epsilon 0. Now it's just the free without epsilon 0, because that's contained in the definition of D. And again, you determine that by doing a little, you have a surface, and then you do a Gaussian pillbox around the surface. You bring the Gaussian pillbox depth to 0, and that's just like D perpendicular above minus D perpendicular below, contains charge with a surface density sigma. Okay, so you already see where this equation comes from. It's just using this on a surface with free surface charge density sigma F, doing a little pillbox, and then taking the height of the pillbox to 0. You get that the difference in D perpendicular above below is just sigma free. And if you now use this one here, but now do what we did before, but now with Stokes' law, so I just have a loop going puck, 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 okay? Take the loop to 0. Then essentially the only thing I can say now is that the parallel bit above minus the parallel bit below for the displacement is exclusively given by the parallel bit of the polarization above minus parallel bit of the polarization below, okay? Because that's the only equation I have to relate those things. So that means that, as usual, the electrical field has no discontinuity as you cross the surface. So the parallel to the surface component of the electrical field has no discontinuity. Okay? But it could be that you have a material that suddenly goes from one type of material to the other, and then the polarization might have a discontinuity. If the polarization has a discontinuity, then the displacement has a discontinuity. Okay? That's what these things mean. So again, these are just boundary conditions that you would use in various problems to solve. But you can get those things quite easily either from Gauss's law or from Stokes, like we just did. Okay, now just a few more notes. The simplest dielectrics are linear and isotropic. So what does that mean? In mathematical language, it means that the polarization is simply proportional to the applied electrical field. And this constant of proportionality, we just put epsilon 0 here, and now we will put another thing here, chi e, which is called the electric susceptibility. Okay, so susceptibility, you know the definition. It's a very well chosen word for this kind of thing, right? Propensity to react to like external stimulations. Okay, so linear, that means that the polarization is directly proportional to the applied field. Isotropic means that it doesn't matter in which direction you apply the field, the material will polarize in that direction. Okay? Now, this is by far not the case for all materials, but the simplest materials behave like this. Okay? In fact, most of the really interesting materials do not behave like this, but we'll get back to that maybe later. Okay, so in these, what we can do is, you see, because we say that the polarization is directly proportional to the field, we can simplify our equations a little bit, because the displacement, which is just epsilon 0 E plus P, so it just becomes epsilon 0 times 1 plus the susceptibility times the field. Okay? And this we can rewrite as saying that the displacement is just the epsilon times the field, right, where this is called the permittivity. Which I find a less well-chosen term, but unfortunately I can't change history. That's what it is. Yeah, and nota bene, so if you have the ratio of the permittivity to the vacuum permittivity, this is epsilon r, you know, the relative permittivity. Okay, just nomenclature for these things. So these linear isotropic dielectrics are the most, you know, typical ones in the exercises that we'll do. So you can almost take it for granted that that's will do. Okay. In the notes, there's a nice example, which is example 4.5, and this is on page 411. It's a sphere of radius A with charge Q, and it's surrounded by a linear dielectric up to radius B. Again, actually, I'm going to leave you to look at it because it's It's a very straightforward thing. You're asked to compute what the field is. Assuming that it's a linear dielectric, it's quite simple because you can just compute the displacement, and then knowing the displacement with the permittivity, you can compute the fields. With that, you can actually compute also the bound charges. You'll get charges on the inner and outer surfaces of this, the sphere, and then there's the dielectric on top of it. So there are two surfaces for this dielectric that contain bound charges. You'll see you can easily compute these things. Okay, and then I think boundary value problems with linear dielectrics. This is also quite. I'll let you read that. It's quite straightforward. There's other examples in there. I mean, please just read the notes because the examples are quite useful. They're just single applications of what we've just seen, but they're quite useful. Maybe what I want to do just upon finishing is just a little last bit, which concerns energy in dielectric systems. Okay, so what we had really is that you remember that the total work to assemble a system, we had done this calculation. You bring charges in from infinity, and you compute what you get. So the energy accumulated is just minus the work you're doing, which is minus the force integrated over the displacements that you're doing. Now, the result of this was that if we just had these point charges generating electrical fields, then we would integrate over the volume of our space the electric field squared. Okay, and that was the energy, as if the energy was contained in the field. And the case for in presence of dielectrics, we can do a similar reasoning. Namely, that let's bring in a charge delta rho f from infinity. Okay, so the work done for this is some delta w. With what is it? Well, it's essentially that I have a present potential, a V of R, and when I bring in this little delta rho, the energy that I have associated to that is just delta rho times the potential. Okay, so if I have this little charge distribution there, what I want to do to compute the work, I need to bring this extra charge there. Just integrate this little delta rho of R, delta rho free, times the potential at that place. And that gives me the increased amount of energy in my system. Okay, but what we have, that rho free is just the divergence of D. Okay, so really the delta rho free that we had is just the divergence of the change in the displacement that we had. And now we can just substitute this. Okay, so it's a simple calculation. So the delta W is just the integral d tau of the divergence of delta D, okay, times V. And that you can just manipulate a bit, because you see, so you've got the, you can do an integration by parts. And use the divergence theorem. So that gives you two terms. The first term is the integral d tau of the divergence of delta D times V minus, minus the integral d tau of the delta D times grad V, but grad V is just minus E, okay? This term here becomes a surface term of delta D times V, but goes to 0, this term here, right? At infinity, so we just keep this last term here, okay? So the delta W is just the integral d tau of delta D dotted into E. Okay, and now you can just you know, so this works always, and now for linear dielectrics, and I'm finishing with this, delta W is just the change of 1/2 the integral d tau of just D dotted into E. So really the work done to assemble the whole thing is 1/2 integral d tau of D dotted into E. Okay, there are some cool problems that that you can solve by just computing the changes in energy of the system. But I'll give you these problems. Actually, what I'll do is tonight I'll just post a little page with some suggested problems for for next Monday, by next Monday. I'll do that later today. Okay, but that kind of covers the thing for now. Okay, thank you.